Take the first 4 multiples of 2. Evaluate the remainders mod 5. Multiply all these congruences. 1, 2, 3 and 4 are relatively prime to 5, so we can cancel them out from both the sides. Finally, we get 2 to the power 4 congruent to 1 mod 5. What we did is the underlying idea behind Fermat's little theorem. So, Fermat's little theorem says that if p is a prime number and a is a number not divisible by p, then a to the power p minus 1 is congruent to 1 mod p. Here is the proof. Suppose that p is a prime number and a is a number not divisible by p. Now consider the p minus 1 numbers a, 2a, 3a up to p minus 1 times a. We can show that no two of these numbers have the same remainder when divided by p. Indeed, if ma is congruent to na mod p, then m is congruent to n mod p. But this is impossible if m and n are unequal and both are less than p. Therefore, when these p minus 1 numbers are divided by p, we get the remainders 1 through p minus 1. And each of these remainders are represented exactly once. We need not know which number will give what remainder, but we know as a fact that when we evaluate the product of these numbers mod p, we get the product of all the p minus 1 remainders. That is p minus 1 factorial times a to the power p minus 1 congruent to p minus 1 factorial mod p. Now p is prime, so p minus 1 factorial and p are relatively prime. Cancelling out the p minus 1 factorial term, we obtain a to the power p minus 1 congruent to 1 mod p. And this is Fermat's little theorem. So now